Bom dia a todos, os que nos ouvem na internet, bom dia aos que estão presentes aqui na Universidade Federal do Ceará. So I will switch to English, since this is our international panel on CO2 capture by adsorption, challenges and advances. My name is Diana Azevedo. I belong to the Chemical Engineering Department here at Federal University of Ceará, UFC. And I have the pleasure to be here with my dear colleague, Enrique Rodriguez Castellón from the University of Malaga, and also Arvind Rajendran from the University of Alberta in Canada. So the purpose of this event today is to present some of the perspectives and challenges concerning materials, how to screen materials, how to shape materials, and with a focus, of course, on application as well. So each of the panelists, I forgot to mention that Carlos Grande from KAUST, Saudi Arabia, is also joining us remotely. So each of them will have about 20 minutes to share some of his thoughts about different topics. And then hopefully we will have a Q&A session, a discussion session, both with the audience that is here and also those coming in the YouTube stream. Okay, having said that, I'm going to invite Arvind to sit on the auditorium, and Enrique, who was the first speaker.
Thank you, Diana. Good morning to everybody. Bon dia to you. This is a real pleasure for me to participate in this workshop on perspective and channel carbon dioxide captured by absorption. I am very happy because the idea of the workshop is very relevant today, because we are going to see many different aspects like material preparation, process, everything. My talk is mainly about how to prepare low-cost adsorbents. And the idea is this is the getting to net zero carbon emission, and one of the relevant points is point number 7, research and development for carbon capture, sequestration, and carbon neutral fuel. And for this, we need adsorbent. And the problem, we have millions of tons of carbon dioxide, we need cheap or low-cost adsorbent. And for the carbon dioxide capture, transportation, storage, and valorization, the first step always is carbon dioxide capture, and this sometimes is the most expensive process from many viewpoints. And for carbon dioxide capture in a post-combustion carbon capture, we have absorption, like the main and more cheaper process. We have chemical adsorbent and physical adsorbent. The main adsorbents are carbon-based material, but there are many other adsorbents with different costs. For example, now you have thousands of papers on metal-organic framework, but this adsorbent you cannot produce tons. So it's very good for public goods paper, but not like for adsorbent of high volume of carbon dioxide. In addition, we have a problem in Europe. If you want to get money from European funding, you have to follow the criteria DNCA, it's do not significant harm. And here, the regulation identifies 6 criteria for determining how economic activity substantially contribute to protecting the ecosystem. And you have to demonstrate that the proposal or material follows this story. And you have the point name is climate change mitigation, the climate change adaptation, and point number 4 is very relevant. It's a transition to the circular economy, including waste prevention and recycling. This is the main point. You cannot use material from direct mining or the using of fuel, traditional fuel. You can read an economy activity but not return a significant inefficiency in the use of recovered or recycled material, increase the data in the use of natural resources, or significantly increase waste of the burning or disposal thereof, causing significant long-term environmental damage. It's difficult, but also point number five, prevention or reduction of air, water, and soil pollution, and finally the protection or restoration of biodiversity. And this means everybody thinks this is a political point. No, it's if you get money, you have to follow in Europe to follow this point. So the conclusion is proposed adsorbent cannot be obtained from direct mining or from the use of fossil fuel. So here we have different examples for carbon dioxide capture, including and the more in this family, more or less the most low cost are active carbon. So what do you understand as a low cost absorbent? According our customer for 0.5 to 1 euro per, but this is competitive. So biomass is an alternative to obtain low-cost absorbent. From biomass, like pyrolysis, you can obtain activated carbon without chemical activation or with chemical activation, depending on the final use of the absorbent. So we propose one study worldwide to obtain charcoal and activated carbon. Why worldwide? Because worldwide are made of cellulose fiber, and this is a problem in many water treatment plants. This clogs the plant, and they need to eliminate, to remove ton and ton. And for example, the United States identified 1 billion annually, according to the National Association of Clean Waste Agency. What I would say to have caused a big issue in New York City and many others, even in Malaga. In Malaga, it's a very big problem because 90% of food material were not intended for wastewater treatment system. Only 7% of what are designed to be recycled. So we propose they use this way for the preparation low-cost accident. First, we need to remove the potential pathogen by bleaching. It's a low-cost treatment. And later, by pyrolytic treatment at different temperature, or by pyrolytic treatment but with a potassium treatment, we have a biocat, activated carbon. So we can identify by Raman spectroscopy the D and G band radio with temperature of pyrolysis, but also by solid-state nuclear magnetic resonance, we will demonstrate the loss of aliphatic carbon and carbon group with the temperature of the pyrolysis. That is where we have the formation of anamorphic graphite. By X-ray photoelectronic spectroscopy, depending on the temperature, we can follow the carbon-18 and the oxygen-18 color level spectrum. It is possible to follow the evolution of carbon and oxygen. That is, carbon content is higher than 90%, coexistence of carbon species non-reduced, presence of water, and low proportion of sodium and chloride species prior to treatment with bleach. And here we have the absorption capacity depending depending of the calcination temperature, sorry, the pyrolysis temperature, uh, showing a higher absorption capacity with higher temperature. This is the limiting micropore capacity and the equivalence of area. It's very high of area. Don't forget that we have a wave, and here we have the electronic microscopy to see the fiber of the material. So we can study that absorption capacity at different temperatures at 500 degrees, 700, and 900 degrees after tested according the temperature increase, temperature taking account of the here is Fortaleza. It's possible to compare the results, and here now we can compare the absorption capacity of the material after chemical activation, which is basic substance. Also, we observe an increase with 20% of addition of potassium hydroxide in comparison with the sample without with thermal treatment. And here, this is the best result with the addition of this basic component. Also, we have studied carbon dioxide and absorption with the best sample, and if possible, the application. This is the more and the potential application is the selective carbon dioxide. Another one application can potential application to verify and here absorption temperature, but also into acid. So remark and this carbon from what what but I don't try to and like we work with the chemical engineering department of the University of Malaga, the collaboration with chemical engineer is absolutely necessary. We designed a low lab plant, pilot plant with 100, 200 kilograms, and finally a 10-ton plant using this way for the separation for removal hydrogen sulfide. It is very successful because this big tower began 6 years ago and already it's not broken. It's fantastic. And we found at the University of Malaga the service of the preparation of adsorbent, because this adsorbent is not only for hydrogen sulfide but also for ammonia. Why? Because with this iron it's possible to capture an acid gas like hydrogen sulfide, but also a basic gas like ammonia. No carbon, no chloride is able to do it. And this is the possible application in treatment of water treatment plant, biogas purification for removing hydrogen sulfide, but also for the treatment is in the for animal farm. It's the main application of this. So we prepared 2 months ago 2 tons in another experimental absorption column for we prepared 2 tons, and this is the installation of the ton because when you have a possible contract with the industry, if you offer a low-cost adsorbent, you have to demonstrate the scientific viability, the technological viability, and the economic viability. We are able to do this, but this point and this are very difficult because you need the support of chemical engineers because you have to design a clear process with simulation, but also finally, the economic viability is fundamental. Okay, another possible another type of waste is cigarette butt. Cigarette butt that is possible to recycle to prepare. Here we have a pyrolysis at 500, 600, 700, 930 degrees. It's possible to observe a very interesting absorption capacity of carbon dioxide. This is the fresh butt, and this is the used cigarette butt. It is more or less the behavior is very similar. If we compare clean and used butt. And also, if you delaminate the cigarette butt with a very easy process, we increase the absorption capacity of this potential absorbent. We have some contact with the time, like the alkaline battery. You need to do the same with the cigarette butt, but it's another possible low-cost absorbent for carbon dioxide capture. And another possibility is the use of cotton cellulose with cellulose and lime cellulose. And in this case, we can prepare a very interesting absorbent with a very interesting absorption capacity for carbon dioxide. It's this type we are talking about residue, no word for eating. It's a cellulose. And find is another low-cost possible absorbent for carbon dioxide, and this is a collaboration with others like Federal University of Ceará. And finally, we want to speak about the polymer. It's a collaboration with the Federal University of Santa Catarina, and geopolymer is a process, very easy, the preparation with low-cost reagent, and it's possible to use application of this geopolymer like concrete, moisture buffering, catalyst, heavy mineral and absorption, and finally carbon dioxide capture. And here, the salt or metakaolin fly ash or biomass ash. There are very different biomass ways for the preparation of this absorbent. And here we compare different absorbents. These are the absorbents prepared with our geopolymer. And here we compare with metal organic framework, geopolymer, the best one from Minelli, and this comparing with a theoretic imidazole framework. And here we can see that we are very competitive. We have an increase of 29%. And this is another interesting point for the use of geopolymer like adsorbent. The main conclusion with geopolymer is that the synthesis of polymer employing residue fly ash, and calcium dry ash in part of composition was successful. Possible quantification of reactive oxide is fundamental. The activator is sodium silicate, the main one, and this geopolymer adsorbent are promoted adsorbent for carbon dioxide capture. And we want to acknowledge the participation of my collaborators at the University of Malaga, our collaboration of Federal University of Ceará. I mean that all of them are here now, except Dr. Enrique Rodriguez, now he's giving a class. And another collaboration with Federal University of Santa Catarina, Professor Moreira, the collaboration of the Institute of Chemical Technology from the Valencia, the group headed by Professor Lopez Nieto, and from the University of Valencia, Professor Benjamin Solsona, and this remain to the work of companies. And this is the Malaga company, and this company is from Catalonia. And here is another one of all university of funding, on Spanish funding, Brazilian funding, commercial funding, very relevant for the study of low-cost access. And thank you very much for your attention. Okay, 20 minutes. 20 minutes. Perfect. Okay, thank you.
Thank you very much, Enrique. Enrique was, I think, one of our first formal international collaborators. So it's been 20 years, nearly 20 years, that we've had the pleasure to collaborate with him. And I forgot to say in the beginning that this event is being held under the framework of the CAPI Sprint Collaboration Project. So both Arvind and Enrique are part of the international team of this international collaboration project. And also, I would like to thank the student Jaiane, who is here. She is within the project of the Brazilian Adsorption Society, so this is also an activity of the Brazilian Adsorption Society. And having said that, I welcome Arvind. Please, Arvind, let me try to put your presentation here.
Yeah. Questions at the end?
At the end, yes. Yeah.
Okay, thanks. Okay, so thanks, Sienna. Good morning, everyone. That's here and online. It's really a pleasure to be here. It's my first trip here in Brazil, so it reminds me of going home to India. The weather, the people, so it's really nice to be here. Thank you so much also for the hospitality. Should also say thanks to Celio, Moises, and the others that I know for quite some time. So what I want to do in the next 20 minutes or so, if I can fill that time, is to talk to you a little bit about the screening of adsorbents. This is a topic that we have been involved in for the last 7 to 8 years in one way or the other. I would say in terms of adsorption optimization, this is something that we've been doing now for about 13, 14 years. And the only thing that I can tell you is that I've come to realize how complex this challenge is, not just to design processes, but also to make materials or even to simulate. So these are fairly challenging problems, so they're not easy problems. I'll say that right at the beginning. So this is my group back in Edmonton, and people that I've not put down here and to whom I'm grateful are, in fact, Professors Farouk Karimi from Singapore that started working on this, several PhD students before that, and particularly 2 colleagues, George Shimizu from the University of Calgary and Tom Wu, that we have been collaborating quite a long time on the topic of MOFs. Just do this, and then I think then I'll be able to use my... Okay, excellent. So the topic that was given to me is adsorbent screening strategies for CO2 capture. And Diana had asked me to talk about figures of merit and process-based. This is a short presentation because I think I'm coming back next week and I'll give you a more detailed presentation. So I try to reduce the overlaps between the two. So if you look at the problem of any adsorption process, not necessarily for CO2 capture, we can think of it in this form. So on one hand, you have pores, which essentially means the material, the adsorbent. It could be like carbons that I would say a staple for adsorption conditions, and more recently MOFs and POFs. I think in the last 2 years, some major advancements have happened in this area, and I'll probably mention it today and talk about it next week. So the other part is, of course, the process, and a lot of engineers here who are experienced in working with these. The two of them come together to make a plant. So you cannot just get to what you want to do just with one. This has to be put together. And what are the advantages that we have as adsorption engineers and the challenges? I would classify them in these following ways. On one hand, we have the materials toolbox. And unlike distillation, where you are more or less, for classical distillation, you're essentially stuck with the potential to separate using just boiling points. Maybe you can add additives to make things better. I think adsorption engineers are pretty lucky because you have an entire set of materials that you can choose from. And just to illustrate the opportunities, I'm using this plot that came out about 5 years ago, where they essentially went to the Cambridge structural database and pulled out all the submissions that were MOFs. So about 5 years ago, they reported close to 70,000 MOF structures that have been deposited. And I think earlier this year, there was another report that put that number close to about 100 to 120,000 actual MOFs that have been submitted. You also know that if you design these MOFs, which are obtained by combining metal nodes with organic linkers to form three-dimensional structures, you can hypothetically make millions or billions of MOFs. And people have compiled these databases, purely hypothetical MOFs that can be built on a computer. So on one hand, we have n number of MOFs to choose from. And if you now are an adsorption process engineer, then you also have a variety of processes that you can choose from. And particularly for CO2 capture, I believe there is an example of each of these processes that are either experimentally tried out or even industrially applied. In the 90s, we learned PSA is better for what we call as raffinate purification, which means purifying the component that adsorbs weakly, whereas you would use TSA for the heavy component or the extract purification. If you take most adsorbents, almost, I would say 99.99% of them, if you consider at least post-combustion CO2 capture, where we are primarily looking at CO2 and nitrogen, almost all adsorbents will adsorb CO2 stronger than nitrogen. So ultimately, CO2 becomes the heavy product purification. So you're interested in targeting the heavy product here. But in the early on, I think there was a very famous report that came from Monsanto that essentially first said that adsorption won't work. And then Paul Webley from Australia showed that there was some critical issues with that analysis. So he corrected that. So there was a lot of work that went on PSA, VSA. In fact, Zeebeck actually has a plant working in one of New York's tall buildings, capturing CO2 using a PVSA process. Also, if you look at Air Products Port Arthur project, which was a CO2 hydrogen separation, that is a VSA process using classical zeolites. But over the many years, we've also started looking at temperature swing adsorption, and that is a commercial process by Svante, which uses a MOF for CO2 separation. Right? And also, we have heard a lot recently about electric swing adsorption. There is also microwave. So there are many ways in which you can do the regeneration. And a lot of these techniques are in particular being discussed for direct air capture, where we are trying to remove CO2 from 400 parts per million. Once you fix this, you can also choose to work with any of these. One is fixed beds, the classical ways in which adsorption processes are run. Moving beds, in which a lot of work has gone on here in Fortaleza. Actual true moving beds, so you actually have the solid trickling down. And then you also have rotating beds. So this is the process that Svante uses with the structured bed that rotates between adsorption and regeneration cycles. So once you fix this, then even the advantage of an adsorption cycle is you can combine individual steps and create complex cycles. And you can know that depending on how you combine these cycles, you can get better performance using the same material. So which means as an adsorption engineer, you have to find the best marriage of the material and the process in order to realize your target. So this is essentially the challenge in front of us and the opportunities if you want to look at the other. So let's go back to what is metrics-based screening. Diana and the others have spoken a lot about it. For those of you who are new, we separate the components basically using the differences in affinity. So we are looking at adsorption isotherms. I consider two adsorbents, two gases, A and B. So these are adsorption isotherms. So A typically happens to be CO2. B typically happens to be nitrogen for post-combustion CO2 capture. These are straightforward to measure because you can go to the lab. There are automated machines. You press a button, and then if you're lucky, in 2 days, you get all the isotherms at different temperatures. So this is easy to measure. So at the end of every adsorbent manufacturing or an adsorbent scientist will usually stop more or less here by measuring adsorption isotherms and possibly heats of adsorption. So this is easy to measure. And for a long time, we used several of these metrics in order to say whether an adsorbent is good for a certain application or not. And you can think of several values, and I'll talk about at least two of them. The most commonly discussed one is selectivity. So in other words, the ratio of affinities between two gases on a particular adsorbent, strong over the weak, typically. So, and if you go into an adsorption class, they will tell you that you want to have high selectivity. And if you think about it for a moment, yes, high selectivity is good, but really good selectivity, okay, we'll see that in a moment. But working capacity is another one between your two adsorption and desorption conditions. What is the difference in the loading? You want that to be fairly high because you want your equipment size to be small. That translates into productivity. The other one is, of course, figures of merit, so which means you can actually combine a lot of these. And people have described this, many figures of merit. And there has been claims that they actually predict what happens at the process level. And in 2016, in this paper, a former student of mine, Arvind Rajendran, who is now a professor or lecturer at the University of Manchester, we asked this question: do adsorbent screening metrics actually predict process performance? So the way that we did was we took 3 adsorbents, we looked at all of these figures of merit, and we also performed a process optimization based on rigorous process simulations. And the short answer is no. Adsorbent metrics are good, but do not use them for screening because they have their limitations, and I'll talk to you about why they are. So what this also means is that detailed process modeling and optimization is required in order to do the screening. The adsorbent metrics tell you the adsorbents that are bad, the ones that you can conveniently throw away. But if you're now dealing with selecting 2 or 3 adsorbents from a group of about 10,000, 20,000, then that does not become a great way to do this. And again, I always refer to this recent paper for those of you in the audience. This is a paper that came out last year from the groups of Lev Sarkisov and Stefano Brandani. This is I think a 50, 60-page review paper. So if you're someone starting, I would urge all of you to read this. This is a very, very important piece of work that connects what happens in characterization with process. Now, why figures of merit don't work? And let's just take a few moments to do this. If you go to an introductory PSA, TSA, or even an undergraduate class, you'd be told that a PSA process works between a high pressure and a low pressure. And they will show typically an and also you'd be told that for a temperature swing adsorption process, you exploit the fact that adsorption is exothermic, which means at a higher temperature, you have a lower loading. So which means if I increase my temperature, I can regenerate the bed. You talk to any adsorption engineer, they will immediately tell you that PSAs don't operate at constant temperature, which means you never work on exactly the size of them. And they will also tell you that PSAs don't operate at constant pressure. At least not constant partial pressure. So, which means, while this is a very illustrative diagram to think about how adsorption, you would all be using these simple and the others. But just for about select that got relative volatilities in distillation, we continue to use this. In simple words, this is the ratio of the affinity in the adsorption and desorption. But if you think about this, if I want to double the selectivity of a material, I can, for example, increase the affinity for CO2, right, and with the same nitrogen. Or I can reduce the nitrogen by half while keeping the same CO2. If, let's say, if we had the powers to do so, we can do it in multiple ways. Both of these will give you twice the selectivity compared to your reference. Okay. So, but if you now ask, okay, what is better when you put it in a process, you will immediately find out that it is always better to make nitrogen weakly adsorbed as compared to making CO2 strongly adsorbed. So because you know that we have usually fixed surface areas, so if you're increasing affinity, you're essentially making your isotherm sharp. From an operational perspective, I need to go to extremely low vacuum that is almost unattainable. So those kind of information does not typically show up in these very simple metrics because they don't tell you much about what happens when you have to build a process. And consistently, we have seen that at least for CO2 capture, at least with the pressure swing adsorption, the best materials are the ones that have almost zero nitrogen affinity. And that is also important because if you're someone working in this area, always please report also the nitrogen adsorption isotherm because it is very, very, very important. It is, in fact, I would say as important as the CO2 isotherm. Right? We are dealing with the separation problem. The other reason why I believe metrics work is because in a process perspective, you're also trying to evaluate under constraints. I need to achieve a certain purity, I need to get certain recovery. So these don't give you that information unless you actually put them in practice. Right? So I can have two materials. One could give you 70% purity at a lower energy consumption. Maybe the other one gives you higher purity at a higher energy consumption. We cannot put them on the same plane. We have to keep something fixed, and typically they show up as constraints. So those have to be fixed in order to compare materials. Right. Again, as I mentioned, metrics are, in my view, the answer is because they don't capture the complexities of a process very well. Now, why move to process-based screening? If you go back to what Sivaji Sircar, for those of you who do not know Sivaji Sircar, he is one of the most famous adsorption process engineers that came out of Air Products, hundreds of patents, essentially revolutionized oxygen VSA. He's no more, but he repeatedly mentioned that a successful gas separation process is generally a good marriage between the optimum adsorbent and the process design. So if you go to the industry, each process is tuned to the particular adsorbent. Even if you think about oxygen separation, if you use sodium X, calcium X, and lithium X, the process operations are completely different. Lithium X is a VPSA, sodium X is a PSA, calcium X is a VSA. All doing the same job, but depending on the adsorbent, I need to tune. So just by looking at isotherms alone, we cannot say much. So that's the point here, right? The other reason is the big bottleneck so far was computing processes was challenging because it involves solution of partial differential equations. But what has happened in the last 4 to 5 years or more is that has completely changed, and computing has become better because we now have access to better numerical techniques. There are more inbuilt optimization tools that are coming out. So these are easier for us to implement. Computing is faster, as shown here. For example, the cost of computing, I would say, has dramatically dropped, even in the log scale. Access to parallelization is easier. I can, without too much of an expense, I can buy a computer with multiple cores. So if I have to do optimization, I can parallelize. A lot of the software tools allow you to do it without having to learn sophisticated languages. And it is cheaper. And probably next week, I will be able to talk to you more about this. Machine learning is, in my view, a complete game changer in this. So what used to take us millions of computational hours can now be done in hundreds of thousands. So you can actually go for lunch and come back and have the answer. So it is so powerful. And I think these are really going to change the way that we can process this. And I will talk in the Brazilian adsorption meeting about this. But also, why this is important is we need to, if CO2 capture has to have some impact, we need to move to scale very quickly. We don't have too much time. And we know that a process will take at least 5 to 10 years to go from the lab to being full scale if you're lucky. So that is an accelerated time. So we need to do this fast. Why move from process-based screening? I think because now we can. This was not possible a few years ago, but now I think we have the tools required to do this. Does process screening work? The answer is, of course, yes. And we have shown this in multiple cases. And what we have here is essentially a framework where you measure material properties, and then we run it through process simulators with optimization. And then we take the output of this and we try to scale up processes. And this is an example from Calf 20, CO2 on Calf 20. This is a paper that just got published 2 months ago, where we make measurements in the lab of CO2. What I've not shown here is nitrogen, but it is also in the paper. And then we run it through these process optimization, where we run full models in order to identify the trade-offs between purity and recovery. And we find what are the optimum Paretos, and we can pick these points and then implement it on a PSA system. And you see that the experiment actually gives you really good results. So this is possible now, right? So yes. So does it work? Yes, but provided you have good data. And this becomes absolutely critical because a lot of what you do computationally depends on what you do either in an experiment or if you're a molecular simulation. And now that we are working with people who do this for a living, I'm learning to understand that even molecular simulation is not easy. There are so many uncertainties that show up. So, but if we have good data, I think now we are in a time where these tools are reliable. Okay. I think this is probably my last slide. Of course, the skepticism is, does process screening tell us the full story? And if you look at what are the desired features of an adsorbent, I would say, of course, it has to be able to separate CO2 and nitrogen. If you're dealing with flue gases or if you're dealing with air, water, you have to deal with water. And I'm also putting steam because, as I will show maybe next Monday, steam is becoming very important for many of these processes, right? If you look at, and these two are typically qualities, adsorption-related qualities. Also, Professor Castellón mentioned this earlier. This is typically what we do in an academic lab. We would usually do this, and if the student is patient and determined, they will go on to do water because it takes years sometimes. Steam almost never. And this is where we would usually publish a couple of papers and we will stop, right? For the rightful reasons, because these are time-consuming processes. If you now have to move this into a process, you also need to do stress tests. People in my lab call it the torture test. So which essentially means that it has to be tolerant to impurities. Okay. Oxygen stability is critical. Most amines that have been now called for CO2 capture almost fail in the presence of oxygen. So and that is there seems to be now a tilt towards adsorbents because they are less susceptible to. But this is increasingly important when you now have to scale up. Adsorption options, if not millions of cycles, so physically stable. We need to be able to structure them macroscopically, and you have to have reproducible large-scale synthesis. So the first example of a MOF that has been scaled up, and I will talk about that. So we were a part of that. Now you can make, they've made Calf 20 in 5 tons. So they made about 5 tons of this MOF for SWAT. So it is doable. So scalability of MOFs is no longer, in my view, at least for one material, an issue. So it is possible. Now, what are the desired process features? Remember that there is no universal process. You have to tailor-make the process for a particular application. What is required for a 30% CO2 stream is not the same for 4 or 5%. The scale-up is critical. We need to be able to do it in large scales. And in many of these practical situations, especially if you're thinking about power or chemical plants, they don't have too much space. So space becomes a practical constraint unless you're doing greenfield. Finally, it's not just the cost of the components. The whole thing has to now be cost-effective, right? So, and that is not easy. And that is also the trade-offs that you are expected to do. So if you ask, does process screening tell the full story? No, it certainly does not. Because it only tells you a little bit about this. The whole thing does not show up. but I think it can significantly reduce the efforts in order to try and fix it. Okay, I'll pause here and I'll pass it to Carlos.
Okay, thank you, Arvind, for this very enlightening talk. For those watching us, we will have a 2-minute or 3-minute break so that we can try to connect with Carlos and hear him here in the auditorium and over the internet. So just 2-minute break.
Okay.
Liguei aqui.
Quer sair ao banho? Liga. Yeah. Then I went to the UK. So you don't drink coffee. When I take some sample, places of the majority is coffee.
O som vai sair pelo...
É um cafezinho? Água, eu vou pegar. Eu tenho na minha sala.
Agora estou a ouvir. Alguém está a ouvir?
A minha câmera não vai.
Mas eu estou a ouvir a Diana.
Ele tá paradinho aqui para mim. Engraçado, essa bicha aqui é como se tivesse. Olá, Carlos.
Olá! Tu não
Fala.
consegues ouvir? Estou a falar.
Ainda
Estou a
não
mexer
chegaste
e a
aqui.
falar. Caramba.
Áudio.
Settings.
Não, aí sim, padrão.
Áudio. Default. Não está tudo bem do meu lado.
Alto-falante.
Testa.
Carlos.
Eu estou a ouvir. ¿No está a
Yes,
ouvir?
we can hear you now. Speak.
Yeah. Estou a falar,
Speak
estou a
again.
falar. I'm speaking. Hello, good afternoon.
Como é que a gente faz?
Salam alaikum.
E a apresentação. Aí eu compartilho. Tá?
Carlos, can you please podes enviar a sua apresentação para
O WhatsApp.
o WhatsApp da
WhatsApp
Jaiane?
eu não consigo. Por e-mail?
Ou e-mail.
Ou e-mail?
E-mail. Ai, vai demorar um bocado.
Eu acho que está ruim. Ó.
Eu acho que ele não tem como apresentar.
Será que não? Se ele...
É porque eu acho que quando você entra com convidado, você não pode apresentar a tela, só o host.
Ah, ok.
Tipo, a gente consegue, mas ele não.
Mas eu já consegui partilhar.
Você conseguiu partilhar aí, está vendo?
Já?
Mas não nos chega por alguma razão.
Não, mas não tentei agora.
Pra gente.
E agora?
Ah, deu certo, deu certo.
Deu certo.
Perfeito.
Perfeito.
Uau, ok.
A gente vai fazer, ele pode começar.
Está em tela inteira para você?
Agora tá.
Agora. Sim. Ok. Só um momentinho, Carlos, que eu vou te apresentar e depois você entra.
De novo.
Só um pouquinho.
Não, eu tirei. Já por aqui mesmo.
Okay, now we are back to the third part of this panel, and then please don't leave. We will have the Q&A session, the discussion session. And now it is my pleasure to introduce Professor Carlos Grande from KAUST, who used to share a room with me when we had our PhD in Portugal. So welcome, Carlos, to the world and to Fortaleza. We're very pleased to have you, and the floor is yours, or the screen is yours.
The screen is mine. Thank you very much. Boa tarde. Aliás, bom dia, Ali. So I'm going to talk a bit about the importance of adsorbent shaping. We had two important people talking before me, so it's very nice to be here. I like the talks of Enrique and what I could hear from Arvind, because I had to restart the computer in the middle. This is very complimentary. I try to make this presentation a bit more basic. So first, like talking a little bit about adsorption process, more on the fundamentals. When you have to go outside to tell people from industry that never saw an adsorption process in their lives, it's very hard to tell them what an adsorbent do, like how to regenerate, and then you suddenly realize a very simple image. You intake adsorption, then you put it out, and it's desorption, and it works cyclically. Indeed, it's the same as a heart. It also works cyclically, and it's very difficult to convince them in another way that you don't want to think about steady state. And when you put that, you really convince them, I don't want to work in steady state, because basically it means the patient is dead. So this is a very good idea that I had some time ago to try to understand that at least part of the oil companies to understand how this works. But then you can tell them, but this is also cyclical with temperature, so it's not just the pressure. And to make this work in a better way, we have to make sometimes the complex a bit difficult. So this is a polybed for hydrogen separation that we try to implement it also for methane upgrading from natural gas. So look at this context. I mean, this is where an adsorbent has to be. So now we cannot use powder this is what the kind of material we are synthesizing, we cannot use a powder, we have to shape it. And we have to shape it to take the best properties of the material into account. How we evaluate that? Well, we have to make a cycle. And this cycle is basically the same as solving a magic cube. So you have to solve a magic cube, but not with, let's say, not with 3 columns and 3 steps, but in principle, an unknown amount of columns, an unknown amount of steps, and most of the times not symmetric. So this makes the process a little bit more difficult. And what has to be understood is that this cycle has to be optimized to maximize the performance of the adsorbent. So the modeling people, kind of like all the people that design PSA, the only thing that has to do is try to maximize the properties that we get from the adsorbent. How we do that? Well, we put complex mathematical models. I will not talk in details about this, but only after that we start thinking, okay, now we have something that we can take to industry. In the case of Arvind, for example, with CALF20, and in other cases we've been trying to do the same. You start with a crystal, you characterize the isotherms, you characterize the diffusion, and after a certain point you have to scale it up. Whether you do it continuously, whether you do it in batch, whether you do it in parallel batch, that's another story. But until that point, you only have a lot of material. You still cannot use it industrially. For that, you have to shape it. The thing is, if you're going to shape it for a very bulk application, probably the simplest thing to do is to pelletize it. There are very simple techniques for doing that. The problem is that when your application becomes very big, when you have pellets, you have a lot of pressure drop. So in that case, you want to have honeycombs. The honeycombs will minimize the pressure drop. If you make these channels a little bit thin, you will not have so much diffusional limitations, and then you can think about having more or less the same performance, but with a lower pressure drop. Lately, and although I'm not very big fan of these techniques for things like CO2 capture, but now you can print adsorbents, as long as you can demonstrate that there's an added value on the shape of printing, that's a feasible technique. So only after you have something that basically doesn't pass through a filter, doesn't destroy one of your valves, you can think about modeling, you can think about using it for different kind of processes, PSA, TSA. In all of the cases, you have to be careful, because particularly when you're using a TSA, especially if you're using a honeycomb, your column will expand, but your adsorbent will probably not. So you might have some preferential ways around the honeycomb, and you have to try to isolate it, and then it gets a bit difficult. I'll try to show some examples. We've been doing this in order to electrify a process, a CO2 capture process some time ago. We have started with a composite material. You look at this material, and it's actually 22% polymer, a polymeric resin, and the rest is a zeolite. So you're talking about a material that has 78% zeolite, and after you carbonize it, you get this kind of color. So it's activated carbon plus 80% zeolite. So here you see 2 materials. There's one paper from the group of Paul Webley that I also co-author. It has been done with this material. We kept the other one. So there are 2 different compositions that the amount of activated carbon in the sample changes, I think, 1.5%, but the electrical conductivity changed one order of magnitude. Actually, it changed 25 times. So this is another version. So this was done by extrusion. We extruded the cold mold, and here what we have done is we have extruded activated carbon and zeolite 13X, and here we have extruded activated carbon and UTSA 16. So it's a MOF actually. We have tried to put these materials in columns. It's a bit difficult when you're talking about rather small scale, and you're working with cubic adsorbents. In this case, it was also a cylindric adsorbent. It becomes a bit difficult. This is the idea that we had to lock them inside the column so that we avoid bypasses. So we have also attached here some silver ink to provide conductivity. and in between here, there was an intumescent material that can actually comply the expansion coefficient. So we pack this inside this column, avoiding also short circuits with the column. I don't know if this video will work, if I have this here, but you can see, I don't know if the screen is very big, but this is a very raw video that we made when we started putting 80 volts. You can see my finger here starting, and the temperature increases 30, 40, 43, 46, 50. We really achieved something like 120, 125 degrees in order of, I don't know, 30 seconds. So it's really unbelievable what you can do when you can get a good conductivity through these adsorbents. So the absorption goes really, really, really fast. The problem is that when you have so many measures to avoid, let's say, thermal expansion and gas bypasses, you are isolating this material so well that you can cool it down very properly. So you have to end up making a cycle to reduce the time for cooling down. And obviously the process becomes a bit efficient, but you use a lot of energy. And also you have to take into account that this is, let's say, primary energy. So we have to take into consideration that with primary energy, we're basically consuming 5 times the power that people is using with residual heat. And so electrification, okay, but remember the equivalence with the heat. Then we can do some modeling, and this is actually quite interesting to do in the newer versions of CPROMs, for example, when you can really model the full PSA. After you do that, you don't need to take so many considerations at the cycle level. You can actually just evaluate as basically same as in industry, what you have here, what you have at the both exits, what you put at the inlet, and you calculate purity and recovery. And in this case, we demonstrated that with this cycle, for example, with pelletized UTSA 16, we can get a very high purity with a fantastic recovery and just only using 6 columns without the problem of using layers that normally is difficult to control, so that you don't pass the CO2 profile into the zeolite. And this will be a big benefit in terms of process control. And after you do that, what people in industry likes to do is to benchmark your technology, and we did this for the case of CO2 and methane. And sometimes what we have in adsorption processes is that the people who wants to benchmark our technologies, I'll show you with laser, they don't understand that a lot of things, for example, in our case, we will do differently than the amine process, and then the benchmark is let's say it's a little bit biased, I would say. But what I think that is important when you do, particularly when you do scale up of adsorbents and when you do the shaping of this adsorbent, is that you try to focus on making a life cycle assessment, especially if you're doing applications that are related to environmental control. So if you're talking about applications that are related to CO2 capture, you have to realize that you will emit certain amount of CO2 when you're putting your capture plant. And if you tell me that you have to run this plant for 5 years just to compensate for the emissions that you're generating for putting the plant, maybe it's not a good idea. And this is something that has not been done properly, at least in most of the cases. But this is, let's say, a summary of the benefits of shaping. And one of the things that I've been doing in the last times is, as people know, playing with 3D printing. What I like to do with 3D printing is to play with different shapes. And what we started doing is making a very, very simple model, right? So you have a pellet, a solid pellet, and you start drilling pores. And the thinner your pores, the more you increase the surface area. And this is kind of obvious, right? It's the basic of using porous adsorbents in process. The interesting part when you do something like that is that if you start correlating with things that you can find in nature, you will see that, for example, for using adsorbents for making small separations like sugars, like gas separation, metallic ions, you're around these values of molecules of pore needed. So you will need porosity to perform a more efficient separation. But for example, if you go to work in the bio area with red blood cells and bacteria, for example, and to some extent some viruses, it doesn't really matter if you have pores. These elements will just not go in. So what we had thought at that time is like, okay, if we can work in this area with high resolution 3D printing, we can a bit go out from this model of sort of like drilling holes, and we can eventually identify that domain. We're talking about printing between 10 and 100 microns. We can identify a mathematical domain so that we can increase this line. And here, look, this is an exponential, a logarithmic scale. So basically, you increase this exponentially if you can do such a thing. So we started playing around. At that time, it was 2016, 2017. We were starting with some adenovirus 5. We never dreamed that there will be a pandemic, actually, and people will know what is a viral vector. And we discovered a lot of problems in between in 3D printing, mostly because of cleaning and stability of the adsorbent and afterwards surface modification. But what is interesting is that some of these materials can offer extremely high or much higher surface areas than what you can achieve in just normal processes of manufacturing such items. And at the end, we generated a monolith with a very homogeneous pore structure that was kind of produced in a, let's say, small scale. It's a 1 cubic centimeter. At that time, it was produced to be retrofitted in one General Electric healthcare column for purification of adenovirus. So I think that this is a potential new world for shaping adsorbents, and I hope we can progress in that area. Not really probably targeting CO2 capture, but more targeting bio applications, places where if we do something like this and we increase the recovery, let's say on 10, 20, 30%, we can increase the value of a process significantly. So with this, I have to thank you, and I hope we can interact somehow. Also, since you may know I'm kind of new in KAUST, if someone wants to make a PhD here with us, you're free to contact me. And I hope we can start collaborating more with the Zara people. Thank you very much. I hope I was not talking to the atmosphere.
Jayani, how do we do it?
Essa tela acho que é minha configurações, professora. Áudio. Aí, isso.
Qual será?
Tá. Peraí. Tá como se fosse do MacBook, né? Tira aqui e vamos ver se aparece o outro padrão. Mas bem que tem que continuar. Não.
Aí.
Deixa.
Vai ser aqui, né?
Aí qualquer coisa eu boto no notebook central.
Okay. So let's go for our Q&A session. I think the microphone will be here. So if you can't hear well, I think you can all hear.
Hola, Carlos. Hello.
Hola, Enrique.
Ciao, Carlos.
Hola, Arvind.
So The session is open. If you want to make your question in Portuguese, that's okay. We can, translate, or Spanish, or whatever language, except Arabic.
Yeah. Thank you, Diana, for inviting me for this very nice seminar. I am not an expert on that social, first thing, but I have many curiosities.
Briefly introduce yourself.
I'm Sonia Cabral de Menezes, and I'm a chemical engineer, but I worked for almost 46 years at the Research Center of Petrobras. So we have some collaboration at Federal University of Ceará as well. And I'm expert on NMI. It's nothing to do, but anyway, I'm involved in the CO2 capture and storage thing in Petrobras when I left. So I'm very curious about the subject. So the first question came to me is what Professor Arvind mentioned, because you mentioned your material is very good for CO2 and nitrogen, but most of flue gases has many things like water, for example, and SOx and NOx and CO that can compete on CO2 for the material. So are you planning to test your material for the real gas, flue gas? That's the first question.
Maybe I can just repeat the question for the audience that is hearing us. So that's the question from Dr. Sonia Cabral. She's a retired scientist from Petrobras, and she's asking about the effect of other contaminants present in flue gases like water vapor, NOx, SOx. So maybe the three of you could comment a little bit on it. Arvind?
Well, maybe Enrique can say it's about the contamination. Well, this is a critical task. It's a critical task because one thing is the lab, where you work with pure gases or mixtures. But when you are going to a water treatment plant or to a petrol company, you have many problems. The main problem comes from the presence of water, this is one, and the second one, the presence of other hydrocarbon. Other hydrocarbon, like hydrocarbon, sometimes the adsorbent it collapses, it closes due to the carbon deposition. So I mean that it's critical the design of the adsorbent. For example, you have to avoid high acidity, or you have to avoid high basicity, or you have to avoid high temperature process. But finally, the problem is what is the operational time of the adsorbent. Depend of the process. In my experience with chemical engineers, they simulate, but finally, sometimes the simulation is okay. They say this adsorbent is for 1 year, and finally it's 8 months or 30 months. But sometimes they fail it totally because the flue has a lot of hydrogen sulfide or many light hydrocarbon. It's very difficult because this information is normally is not provided from the industry because sometimes the chemical composition of a flue is variable. So it's difficult to simulate or to design the adsorbent for different conditions. So, in my opinion, it is necessary a univocal connection between the industry and research in order to design the adequate pore structure of the adsorbent, in order uh, to optimize the best condition. But sometimes, depending on the process, it's very difficult because the composition of the flue is not homogeneous. And this is my opinion, the main difficulty. Do.
Yeah, well, I agree. I think when it comes to CO2 capture specifically, as you mentioned, SOx and NOx are important, but I think we should also not forget oxygen, especially with amine-based adsorbents, which are probably the most advanced, at least for direct air capture. Oxidative stabilities are poor. So, and there have been some really interesting materials that came out with very interesting isotherms, but from what I hear, when you put it in oxygen, it collapses essentially. So oxygen itself can be a big issue. So there, in such cases, there seems to be a preference towards physisorbents. Then, of course, water can be a disaster. Mobs and Carlos has very graciously warned me about certain mobs. Some of them completely collapse, the structure collapses, and some of them even dissolve in water. And Carlos warned me about a particular MOF, which was considered UTSA, for example, is a very important MOF that has been identified as high performer. But you show it to water, and Carlos was the one who pointed me to that, it dissolves. And why is this important? Because you're dealing with moist flue gas. So if you're either doing vacuum or some kind of a steam regeneration, and if water condenses, it could essentially just wash away that MOF. So that becomes very important. So the impurities, in my view, oxygen, SOx and NOx, humidity play a huge role in doing this. For example, in the paper, in the CALF 20 paper that we had published together with George Shimizu and company Svante, I think they did something like 450,000 cycles of just going back and forth with steam, and we had to show that it essentially survives that long. And thankfully, we didn't do it. Svante did it. So and they also did SOx and NOx tests, so they did XRD pattern. So and that brings me to another point which I should have mentioned earlier. When you list down all of these properties that you want, you don't need to be exceptionally good with some of them. You actually need a material that will survive, right? So that often becomes very, and particularly with adsorption, it becomes important because unlike in liquid absorption, and they also have amine degradation, as you know, but there is a way without stopping the process, you can purge and you can add a new solvent. Whereas in an adsorption process, you cannot, right? Especially if it is a tail end process, then okay, direct air capture, no one stops you because you stop the plant. But if it's, for example, pre-combustion or something that is sitting right inside your process, then you cannot afford to do that. That becomes even more challenging. So I fully agree with you. Yeah, I'll maybe ask Carlos to talk about it as well.
Can you hear me?
Carlos.
Yes.
Yep, we can.
Yeah. So I mean, I will take up part of what Arvind said to try to make the rationale of it. As you say, you provided an adsorbent, you provided some data, you showed that it worked, but after a certain time, you have to demonstrate that this is durable. So from the point of view, let's say from Petrobras or from other people, when you evaluate this, when you pass a gate technology 1, 2, 3 or something, you have to make that study. And in between, when you make the cost assessment, you have to put something called contingencies. So this is a place where you have to take a contingency. If the adsorbent lasts for 1 year, you have to evaluate whether you put a pre-bed to avoid contamination in the adsorbent. You know it will cost you some more money, but it's doable from the engineering side, etc., etc. So it's just a contingency. Obviously, if the contingency is something that demonstrates that your adsorbent will last 1 month, nothing to be done.
Celio?
Can you hear me?
Yes.
I will speak from here so you don't see me. Thank you for 3 very nice presentations from Enrique, Arvind, and no, thank you.
Come on, Celio.
Who's following me? And thanks, Gianna, for organizing this for our Brazilian Adsorption Society. I just would like to take one point that I would like your comments from the three of you. And maybe Sonia can help as well, since she's a materials researcher. In the last 10, 15 years, we've seen thousands, millions of MOF structures. And so far, we haven't seen one single, as far as I know, process application, industrial application. Recently, we heard from Canada for direct air capture. Is it direct air capture?
No, it's from cement.
Yeah. So
Cement industry.
yeah, so yeah, that's how I want to proceed with this comment. And finally, it seems that we're getting out of the lab scale to the industrial scale. And I still believe there might be some concerns about cost, stability, long-term endurance, and everything. So that's a kind of comment, because so far we've seen mainly, people in the lab with the MOF, but the real world going for still with zeolites and other materials. So how and I think the Arvind and Carlos' work in coupling the materials with the process in a optimization target will help guide industry applications for, nowadays it's CO2, but potentially any other adsorption process that's being used with, let's say, ancient zeolites and ancient materials.
May I add something to that? And when I hear Carlos reply to that, one thing that you mentioned is that 3D printing maybe has something to show, or an advantage for chromatographic operations, and maybe CO2 capture will still rely heavily on the old beads and pellets. So I would also like to hear something about that when you comment on Celio's question.
Okay, so maybe I'll give you some background with this particular MOF that has been scaled up. And I don't have any financial interest either in Svante or in the MOF, so we just happen to characterize that material. So this is a zinc-based MOF with oxalate linkers. And from what I understand, both zinc and the oxalate are cheap elements. So that is the first thing that you have to start with, nothing exotic. And BASF is their commercial manufacturing party. So, and they were also part of that paper. So BASF has so far scaled it up. They've made about 5 tons of calcium. So that is what we understand. And I think they make it in 300 kilograms, or I've heard that they've even been able to do 1-ton batches. So the MOF scalability has been shown. Of course, from what I also hear, it is not easy. But what BASF tells us through the paper is also that it's scalable, and the throughputs that they're seeing are comparable or even better than zeolites manufacturers in that case. So this is a material that has been in a TSA process, and I think in my view, it's a temperature concentration swing, because in Svante's process, they use steam, directly inject steam into the material. So the material also has to withstand high temperature steam. And they have implemented this in 17% flue gas from a cement plant. So that's where they've been testing for the last about 2 years. And they say that the performance has been good. The cost of the MOF, as they reported in the open literature, was about $20 to $30 per kilogram.
How many?
$20 to $30 a kilogram. That was publicly, this was before the pandemic. So, and the reason why I say before the pandemic is for those of you who are looking for lithium zeolites, maybe Carlos can tell you, it just went from about $15 per kilogram to about $60 a kilogram. So it is in the order of some of the zeolites. So it is being tested in a cement plant in a real flue gas application for the last 1 or 2 years. But like what Celio mentioned, it is one of the several MOFs that have gone through. Now, the other aspect to bear in mind is also the scale. I think doing CO2 capture using adsorption at extremely large scales compared. So when I'm saying extremely large scales, million tons of CO2 per year, which is done by absorption plants, I think that can be a bit of a challenge. Simply because adsorption processes don't scale that well, and you have to build modular units. Svante on their website claim that their adsorbent wheels can do up to 1,000 tons per day, or I think 1,000 or 2,000 tons per day. So that translates into about 300,000 or 400,000 tons per year. So that becomes a scale issue also. So, but on the other hand, if you're looking at direct air capture, adsorbent-based processes seem to be the most mature and the most commercialized. So Climeworks has a 4,000 tons per year. Yes, it's 4,000 tons per year. So it's less than some of our own personal emissions. Right? So it's small. They're scaling it up to 40,000 tons per year, 36,000 tons per year, so approximately 10 times. And there's a company in California which is building a direct air capture plant of 5 million tons a year in the next few years, and that's going to be located in Wyoming, in the US. Again, a sorbent based, most likely an amine, we do not know, but so in addition to all the rigorous tests that we are putting these things to, I think one also has to be aware of the scale at which we can implement some of these techniques. Chemical absorption can, of course, be done at million tons a year, so that is what is being done. So this one material, process, stability, and the scale and the compositions. So on one end, I think at higher concentrations, if we have such flue gas streams, I think adsorption has a place. Our studies have shown that between 13 to 20% typical coal-fired plants, adsorption has less because of the concentration and the scale. At very low concentrations, 400 parts per million, again, adsorption comes back and becomes better. So I think one should not ignore the specific problem that we are trying to solve, concentrations and scale. I'll maybe ask Carlos to comment on that.
I have a mixed view about the whole thing. The scale is a bit of an issue. It's a big issue actually. So it's very difficult to scale up an adsorption process. I mean, when you do the scaling up, the performance is there. Purity, recovery are nice. Energy recovery, energy consumption is probably also okay. And then there comes this time when you have to report how big the unit is. And there you have a problem. Not all the places have a physical place to put a big equipment, even if it's worth it. And I'm trying not to touch about the fact that the whole CO2 capture problem is. I mean, when people is talking about 20, 30, eventually $50 or $100 from direct air capture, so forgetting about the science, okay? Now you are in Ceará, eh? So just go out and just grab a person in the street and how much you will pay for CO2 capture, and there you might get an idea. So if you look at what happens now, it's a very unpleasant term, but it's a toy of the rich kid so far. And there are not so many rich kids in the world, and this is a global problem. So I'm not so sure of the whole efficiency of the approach actually. Regarding 3D printing, Diana, indeed, this is super expensive. So my thing is that it will be the laminates or extrusion, hardcore. So there are big extruders. I mean, I've seen Corning having extruders of 8 meters to produce honeycombs. So that's there already.
No, I have a strong comment. I am very critical about MOF application. The lower price I have found at Instituto Mexicano de Petróleo is a chromium MOF of about $8 per kilogram. But I am very critical for application in big installation. But MOF will be very helpful for pharmaceutical industry. It's a high added value product. In this case, it's fantastic. But for petrol companies, impossible to pay. They are not competitive with CO2. Absolutely. Thank you.
Are there any questions coming from our feed? No questions? Well, Sonia?
I'm not expert in the subject, but besides testing the cycles for adsorption, how critical is the speed of absorption and desorption of CO2 for the material?
That's a good question for students. So what about the kinetics of absorption and desorption? And I would add to that the kinetics of heat transfer as well.
Well, I am not expert in this field because we leave our material to the chemical engineer for doing the kinetic experiment. But depending on the process, we can modulate the space velocity of the pressure. And depending on the process, sometimes we always consider the kinetic of the process. But we used to simulate real conditions because depending on the process, the kinetics are totally different. Sometimes we need a high diffusivity of the material. Sometimes it's 1 hour, no second, and depending on the process. But we always consider the kinetic of the process because the porosity is critical for the kinetic.
Yeah, that's a good question. It was a two-part question. So first, the testing itself, and I think it was last week, Carlos, or 2 weeks ago, that the two of us were exchanging emails about how important is it, for example, to even measure the effect of water on many of these, and how very often those experiments get misinterpreted. And I think that's a major issue, especially when you look at characterization papers. Going to your second question about the kinetics, of course, it has to be very fast. For example, if you look at oxygen in rapid cycle pressure swing adsorption, they're in the order of a few seconds, a couple of seconds, or even shorter. The diffusion times are very quick. In many of the adsorbents that will, unless you're using kinetics itself, and Carlos works on such, but more for methane and other applications, these tend to be equilibrium adsorbents, so they tend to be faster. But if they are slow, then it's also important to understand where those resistances occur. And that's a place where Celio's work, for example, in the ZLC and others, can be helpful. Because only if the resistances are in a certain place, then making either a monolith or any of the beyond the pressure drop advantages that you get become interesting. So kinetics are very critical. You want them to be as fast as possible, because kinetics directly impact the productivity of the size of the plant. Yeah. Carlos?
Fully support that. It's very important to have, I mean, if you're working on removal for CO2 from flue gases, the fastest it is, the better. Otherwise, you will have a mass transfer zone and your equipment will become large. And also you will struggle with purity, so you have to spend more energy. On the other side, if you want to remove CO2, for example, from other places like biogas, where you need to kind of force the adsorbent to not adsorb methane, you want the kinetics of CO2 to be as fast as possible, but without having any adsorption of methane. So in that case, the adsorption of methane has to be delayed, I would say.
And maybe I'll just add one comment. Yeah. The kinetics is important, and I will make a comment at least about this Cervantes rotating wheel process, because temperature swing adsorption has been traditionally considered as slow because you have to overcome the thermal capacity of the material, because it's slow to heat and cool. So Carlos showed that in his electric swing. And that was the primary reason why Diana and Moises studied the moving bed adsorption system, because you overcome that. So in this particular case, so Svante uses a structured material. So it's essentially a carbon fiber on which they coat them off, and then they stack this up into a module, and then you have the gas flowing through that. And this is and then you have a few steps, and it is a 1 minute cycle. So in 1 minute, your adsorption and desorption is over, which is comparable to the cycles that you see in large-scale oxygen plants, for example. So which is a PSA, oxygen PSA plants, it's about a minute or so, it's a cycle time. So they're able to achieve that in a TSA process because, one, they use these fast heat conducting. And Diana also mentioned heat removal. Yeah. And that is absolutely important, because some of these fancy materials that show S-shaped isotherms, double S-shaped isotherms, they're all nice on just to look at them. But the moment you start putting them into processes, it becomes a heat management issue. So kinetics are absolutely important, because you want to switch as soon as you can. Thank you.
Well, I think we can wrap up right now, and I would like to take the chance to thank
have
all
at least
those.
One student asking a question.
Yeah, that's right.
Yeah.
Am I looking at him or her? Well, I think they're shy at the moment, but they will have the chance to ask Arvind and Enrique, who will be here for the next few days. And I would like to thank all the audience that's hearing us online, and all of you that are here, and particularly Carlos, from so far, close to where the World Cup is being held. And Arvind and Enrique, thank you very much for this nice morning spent together. And finally, I would like a warm clap of hands to Jayane, who has been doing all this to make it happen. So thank you very much, and we can continue locally with our discussion.
Okay.
Bye, Carlos. No.
Bye, people. Thank you very much for the invitation.
Now you can have a beer there, Carlos.
It's forbidden. Huh?
There's beer without alcohol.
Poor Carlos.
Ciao, Carlos.
Bye. Ciao.
Ciao.